Thank you for attending today's webinar. Can everyone hear me? David, can you hear me? Joe?
Yep.
Yep, can hear you.
Okay. This is actually the sixth consecutive month we've done our webinar series. Today's topic, we're going to talk about mean time between failure. The title is How Long Will It Last? MTBF Knows, or does it? We don't usually do this, but today I was going to have Joe tell a joke. Joe's from our technical support team. He runs our technical support team in the US. And it's a related joke to the topic somewhat. Joe, do you want to start us off with that?
Sure. Okay. This is a joke that one of our customers taught me at one of our training sessions. I've got a math background, so I get sometimes super technical and super precise, which is really easy to do on this topic. And she was kind of politely reminding me that not everybody has that same need for high degrees of precision, and that some people are more of the close enough attitude. So the joke she told me is that about a mathematician and an engineer, a super precise person and a not quite so, walk into a bar, and the bartender stops them right as soon as they walk in the door. Says, "Wait right there," and he pulls out two steins and pours two beers and says, "Okay, these beers are on the house. They got your name on them, but there's a rule. In order to get your free beer, with each step you take, you can only move half the remaining distance from where you are to the bar. The door's about 20 feet away from the bar." So the mathematician looks at it and just throws up his hands in frustration and storms out and says, "Well, I'll never get it then." The engineer, on the other hand, takes one great big jump and then a smaller jump and then one great big step and a smaller step, says close enough, reaches out and grabs his beer.
Okay. Thanks, Joe. So I hope you like that. Today I'm joined by David Wiseman. Just a quick introduction to David. It's actually Dr. David Wiseman. He has a PhD in nuclear structure. He's been with us for decades now, right, David?
Yeah, well, very nearly two. And it's funny you should mention physics because as a physicist, I'm not averse to approximations either. So
That's good.
we're gonna
That's
be
good to
fine.
know. Yeah, David's been over our training and support for many years in the UK, so he's been exposed to a lot of questions and these conversations on MTBF. David is also a big jogger, and he loves Liverpool football, soccer, for those of us in North America. So, regardless of what you say about MTBF, please don't say anything bad about Liverpool soccer or
Nobody would ever do
football,
that.
or we're going to lose David. Um, just a couple of housekeeping items. You'll see there's a chat menu, there's a questions menu. Joe and Rachel and I will be watching the questions and the chat menu, and we'll answer as many as we can during the meeting. If your questions don't get answered, we will be contacting you to answer your questions after the meeting. And so between the questions and the chat menu, please post your questions in the questions dialogue. I guess there's two different dialogues. We'll try to keep an eye on both, but it'd be nice if we could just keep the questions in the questions dialogue. David, you want to go to the next slide? We did. Can you pull up click on it? There you go. I didn't give it a go a couple times. We did have a list of where kind of people registered from this time based on the website, things like that. And so I realized we have a lot of people from both Isograph and Plato and IQS on this webinar. Just a reminder, we've talked about it before. We've merged into three companies. IONS is the kind of qualitative model-based engineering platform. IQS is the quality center, the comprehensive quality management system. And then, of course, Isograph is the side that we come from, where we do a lot of reliability studies like fault tree analysis, block diagrams, prediction, We do a lot with these MTBF numbers. We use them also in our availability workbench, which is our simulation tool. The future plan is that we'll be creating an online platform that integrates a lot of these ideas into one place so that you can have one source of data, basically, which will help solve problems like data integrity issues, using multiple platforms to do kind of a start to finish design on systems, products, whatever you're modeling. If that's David, if you're ready, let's just get into the presentation, and I'll just chat again near the end.
Okay, thanks very much. Welcome everybody. Yeah, so today's presentation, today's webinar, we'll be talking about mean time to failure. Mean time between failure. Already getting my terms mixed up, which is actually a quite thematically appropriate, as we'll see. I'll keep my camera up. Hopefully that's not obscuring anything important on the slide. But we'll start with a little agenda just to work through what we'll be talking about. Unlike a lot of our previous webinars, this one will rely a lot on slides. We will be jumping to some software tools a little bit later to kind of back up some of the things that we'll be talking about. But we'll begin with some definitions and associated assumptions. So defining some of the terms we'll be talking about, also talking through some of the assumptions we need to make in order for these terms, for these parameters to work for us. We'll be asking the very important question of what does the internet say? I think anytime we want to know something these days, the definition of a term, things like that, we go to Google or, well, other search engines are available, but we pop that in and we get back, well, these days what we get back is an AI generated answer, which is pulled from different sources around the web, and that in itself can cause some problems if those different sources are saying contradictory things. We'll have a simple example, again, pulled from the web. If you've ever Googled MTBF to try and work out what it's all about, you may have seen this example. So we'll take a look at that, and we'll take a look at some of the problems with that example as well, because it does exemplify some of the issues we have with the definition of mean time between failure and our understanding of it. Then we'll look at some what I call more realistic examples. These are examples that have been generated with simulated data to give us an idea of, again, how some of these parameters can be calculated, what might be the right way, what might be the wrong way. And we'll have a little defense of mean time between failure as well, because I know that I think there has been a bit of a movement maybe to not abolish it, but to basically stop using it because maybe it's not valuable or because there's such confusion that it's causing more problems than benefits. So we'll talk about MTBF in a positive light and what it can tell us. And finally, we'll just round off with some conclusions about what we've spoken about. Let's get into it. We'll talk first around some of these definitions and associated assumptions, beginning with mean time to failure. Now, right at the bottom of the slide there, and it's highlighted in red, I've said that terms mean time to failure and mean time between failure are often used interchangeably, and that's why I'm talking about it here. You know, in a presentation about mean time between failure, why am I talking about mean time to failure or mean time to first failure? It's because people don't often know what the difference is. And when you look at some of the definitions, you start to think maybe there is no difference. But as we'll see, there is a difference. And what we'll try to do is kind of remove some of the confusion around that if we can, or start an argument, one or the other. But mean time to failure or mean time to first failure is the average amount of time between startup, or sometimes you prefer installation, so startup, and the first failure. So the first failure of a component. What is the average time between when you start the component up and when it fails for the first time? The assumptions behind this are that failures are random. So failures are random. What this means is if you prefer that the failure rate is constant, there is no burn-in, there is no wear out, the rate at which these components fail does not change with time. So for mean time to failure, mean time to first failure, when we estimate that, we're assuming there is no wear out. And in general, this is a parameter that is applied to non-repairable components. So it might be a capacitor. It pops, you take it out, you put in a new one. Non-repairable, it's replaced on failure. Maybe a bearing. Bearing fails, you take it out, replace it with a new one. So non-repairable failures, and we're assuming that failures are random. A little note also on mean time to repair, which is the equivalent but for repairs. The average time from failure to repair. Now, this is not strictly the same thing as mean time to restore. Again, maybe you could do another presentation on the difference between those. Mean time to repair is the average time from when something fails to when it's fixed, but maybe not necessarily when it's restored to service, which would be your mean time to restore. For simplicity, I'm going to assume that they're equal in this case. Again, an argument maybe for another day. But again, I've defined mean time to failure there. Why? In this presentation about MTBF, am I talking about MTTF? Because these terms are often used interchangeably. So now we come to the slide that I feel might be the most dangerous for my personal safety, which is this one. So mean time between failure. So in general, this is a term, a parameter that would only be applied to a repairable system, not a non-repairable component. We'll see the issues with that later, but to repairable systems. But in the simplest terms, if you Google this, there are, again, these two competing definitions. One is that it is the mean time from when a thing starts up to when it fails. So from the end of the repair to the next failure. So the average time from when the thing is repaired to when it fails again. The other is that it is the mean time between one failure and the next. So including the repair. So one definition excludes the time to repair. One definition includes it. Which of those two definitions is correct? Well, you can see from my slides there, it is the second one. And trust me, I know what the arguments against this are, and we will be addressing that. So I can explain, so please don't leave immediately or post anything unwelcome in the chat. We will be talking about this, and hopefully I'll be able to convince you, maybe not, but that's the correct definition. From failure to failure, not from the end of the repair to the next failure. And we will be showing how we deal with that, what the impact of that is, what the usefulness of it is. So now we come to our question of what does the internet say? Specifically, if we were to ask the internet, how do we calculate these two parameters? How do we calculate mean time to failure? How do we calculate mean time between failure? And I'm not talking right now in terms of complex probability theory. I'm not talking in terms of like fault tree or anything like that. I'm talking about if you collect failures from your system, how do you use that failure history to work out what the mean time to failure is? How do you use that failure history to work out what is the mean time between failure? And often what you'll see is these two fairly simple equations, beginning with the equation for MTTF, the equation for mean time to first failure, service time divided by the number of failures. So the service time, it's worth defining what that means. Service time is the amount of time over which you observed that population of components multiplied by the number of components. So if you watched 100 components over the course of 1 year, the total service time would be 100 service years. 100 components multiplied by 1 year, that would be your service time. So you want the MTTF, you would take the service time and divide it by the number of failures. Fairly straightforward calculation, but not without its problems, as we'll see. But for mean time between failure, it's the running time divided by the number of failures. So the running time is for the system now, because we're not looking at a population of components, we should be looking at a system. Although from the way these equations work, you sometimes wonder if that's really the case. But the running time is the total amount of time that the system or whatever it is you're looking at is in service, is operating, is performing the function that it is designed to perform. So in my little diagram here, it's all these green arrows, everywhere where the system is up and available contributes to the running time. And MTBF, by this definition, which I'm not saying is correct, by this definition, is the running time divided by the number of failures. So two slightly different equations for ostensibly two slightly different parameters. Both of these equations assume that failure is random. So constant failure rate, if you prefer to think of it that way. But there are problems, as we will see. So both calculations have their issues. I think this is actually exemplified, as I said earlier, by this example, slightly morbid example, but I dug it up off the internet, which seems to be where most morbid things come from these days. So this example, if you've ever Googled MTBF and what it all means, you may have seen this example. So we have a population of 500,000 25-year-old people, and we monitor them for 1 year. In that 1 year period, 625 of those people die for any given reason. What is the mean time between failure? So this is the way the example does it, is to calculate, they don't put it like this, but it's a service time. They calculate a service time, which is, as we said on the previous slide, the number of components or whatever it is multiplied by the time during which you observe them. 500,000 multiplied by 1 year equals 500,000 people years, let's call them. Now, the observant among you might already see a problem here, but we will come to that explicitly a little later. The number of failures, such as they are, is 625. So what's the MTBF? Well, it's 500,000 people years divided by 625 people. So the mean time to failure for a 25-year-old person is 800 years. So let that sink in for a moment. So anybody in the audience who's 25 years old, if you're lucky enough, then you can expect a solid 800 years according to this equation. So where are the problems? Well, I mean, the first problem is it's actually not a problem with the calculation itself necessarily. This is something that is addressed in the examples that are given online. The fact that in reality, the average life of a human being, obviously depending on where we are in the world, is about 80 years, let's say. Because, of course, human beings, like so many things, do eventually wear out. And anybody who isn't 25 years old might have an idea of what that feels like. But things wear out. So in reality, we need to keep these things in mind as well, that for that 1 year period, we might be seeing what we call random failures, but later on, we might start to see what you consider wear out failures happening. So that's something to bear in mind. Now that one is a fairly obvious problem, and it's one that's addressed in the example as it's quoted online as well. But there are other problems as well. For one, isn't MTBF supposed to be for repairable failures? Now, I'm no doctor of medicine, but pretty sure that this is a non-repairable failure, unless there's something of which I'm just not aware. So straight away we have a problem. Can this be the MTBF for a non-repairable failure? Well, no. Based on the definitions and assumptions of the previous slides, random failure, non-repairable, using the service time, this is actually a mean time to failure. This is a mean time to failure for a 25-year-old person. It doesn't mean that a 25-year-old person will actually last for 800 years before they pass on. What it means is that, on average, 800 years worth of life would have been lived between a group of 25-year-olds before one of them passes away. But this is a mean time to failure calculation, not a mean time between failure calculation. And already we start to see why these two terms get kind of mixed up with each other when examples online are quoting a calculation of MTBF when it's really a calculation of MTTF. There's another problem as well, though, which is a little bit more subtle and a little bit less obvious. The calculation of service time. Let's say, okay, actually, we found this quoted online, we found this equation, we found this example, and it correctly says that this is the mean time to failure for a 25-year-old person. So it says it's MTTF, that's absolutely fine, but is even that calculation really correct? Because the service time, 500,000 people multiplied by 1 year, is including the entire year of service for every single person in that group, including the ones that didn't make it to the end of that year. So if somebody, say, left us after 8 months, why are we still counting the subsequent 4 months towards the service time when that person wasn't in service, so to speak? So really, should we not be using the running time? That would seem to make more sense, because counting the service time, that's going to skew our mean time to failure in an optimistic direction. So let's kind of break down the problems that we've found so far with this example and maybe all around our definitions of these different terms. So problem number 1, wear out and burn-in as well, but wear out in particular. Our MTTF and MTBF, our mean time to failure and mean time between failure calculations, are working on the assumption that failures are random. And of course, for a human being, maybe in the middle of the life, that's broadly correct. We don't see what we call wear out failures that early on. Later in life, and you'd see the same thing with other things too. Maybe could be a bearing or some other component or piece of equipment that has a useful life where failures occur at random. But then later, you start to see failures occurring because of wear out, because things start to break down as time goes on. Now, this does not mean that all of our calculations must be wrong. Very often, when we do things like fault tree analysis, for example, we see this a lot there. Mean times to failure rates are assumed to be constant. The underlying assumption there is that we're doing maintenance. We're doing maintenance to make sure that wear out doesn't occur. So the failures we do see are only those that occur at random. So it's still a reasonable assumption that we are seeing random failure without wear out. So that's not necessarily a big problem. We can account for that by saying, well, we're doing maintenance. That keeps the failure rate curve pretty flat. So our MTBF and MTTF calculations survive that test because it's a reasonable assumption to make. What about problem number 2 though? Problem number 2 was that MTBF, so mean time between failure, and mean time to failure can be confused with one another. I mean, in this example, we had a calculation of mean time to failure that was being presented as a calculation of mean time between failure. Essentially, we had this population of people and their deaths being treated as a kind of component-like non-repairable failure that occurs at random. So really it was an MTTF calculation and not MTBF. So we can see why there might be some confusion there. Problem number 3 was more specific to mean time to failure. This was where I was saying that when we did that mean time to failure calculation and we worked out the service time, so remember service time, the number of components, or in this case, the number of people in the test population, multiplied by the time over which we observe them to give the total service time, is including the time for each person that doesn't make it to the end of that period. So how can this count to service time when our component is not in service? It failed, it's non-repairable, it's not coming back. Why is that being counted? So it suggests then that the mean time to failure calculation even is not correct either. That's that service time over number of failures. And it's going to skew our calculation towards a more optimistic mean time to failure. Now, I can sort of understand why it's done this way in this example. It's a huge population in the test population, so 500,000 people, of whom relatively small number were lost, 625. So it's still a good approximation whether you include the whole service time or just the running time. The result would not be much different. But in our world, in the world of reliability, when we're looking at the failure and replacement of components, how often really are we going to have that many data points? How often can we have hundreds of failures among hundreds of thousands of components to work from? We're lucky if we've got 20 a lot of the time to do these kind of analyses. So that's where this approximation again is going to kind of start to break down, and we need to be careful of that because it's all very well using this, service time when you've got 500,000 data points to work with. If you've got 15, it's another matter. So we need to be using running time, not service time, even for the mean time to failure calculation. That brings us to the final and perhaps biggest problem of all. So problem number 4, we've established the following based on our definitions and on the little example that we looked at. We know that both the calculation of mean time to failure and mean time between failure are assuming that failures occur at random. So random failure, or if you prefer, a constant failure rate. So things aren't wearing out. Both calculations make that assumption. We've established also that in order to calculate either of these two parameters accurately, whether it's mean time to first failure or mean time between failure, we need to be dividing the running time by the number of failures. And we know that, or at least by these definitions, again, I don't want to say no, because I think at least one of these definitions is going to be wrong. By the definitions we're working to right now, by the definitions and the assumptions that the last example were based on, both MTTF and MTBF are the average time from startup to failure. It's just that MTTF deals with first startup and first failure. MTBF deals with maybe repair to failure. Maybe. But if all of that is true, then that just means that mean time to failure and mean time between failure are the same thing. They are the same thing. Because if these failures are random, then there is absolutely no difference between one startup and another. First startup to first failure, second startup to second failure, 10th startup to 10th failure. There is nothing to distinguish between them because there's no wear out. We're assuming that repair puts this thing back to good as new, such as it is. If either of those things were not true, then the whole approximation would break down anyway. There is nothing to distinguish one failure from the next. First failure, nothing to distinguish that from any other. So by those definitions, MTTF and MTBF would be the same thing. And again, we come back to this problem of how people get confused between the mean time to failure and the mean time between failure. MTTF is meant to be this mean time to first failure of a non-repairable component. MTBF is meant to be the average time from startup to failure of a repairable system or component. But once you've applied all of these simplifications, all of these assumptions, they become basically the same thing. So what's going wrong here? Well, the problem is with the definition of mean time between failure that we've been looking at up to now. We've been saying that the mean time between failure is the time from the end of the repair, so startup after repair, to failure. But that's not what it is. Mean time between failure is the mean time from failure to failure, including the repair. Now, don't get me wrong, I understand what the arguments are against this. The big one is, would that not mean that if I wanted to improve my mean time between failure, if I just wanted to make it so that I have a much better MTBF value, much longer, I could just take my time over my repairs. Instead of repairing something in 12 hours, I could just loiter around and take a week to do it. That would improve my MTBF, wouldn't it? And yes, technically that's true, but, and this is very important, as we said, mean time between failure is not applied just at a component level. If we were to do this for a component, look at the mean time between when, say, a capacitor fails and when it fails again, then I could certainly increase that time very easily by just very slowly taking out the failed capacitor, very slowly putting in the new one. But we don't apply MTBF to components, and certainly not to non-repairable components. It's applied at a system level. And I will show you what the significance of that is shortly. But right now, we need to remember is mean time to first failure, MTTF, is the average time from startup to failure of a non-repairable component. MTBF is the mean time from failure to failure of a repairable system. So not a component, but a system. So we will address that question of MTTR, mean time to repair, a little bit later. For
David,
now,
can I just jump in on that point real
sure, yeah.
quick? Just one thing also to point out about that MTBF is that it doesn't exist in a vacuum, right? So it is true you can improve MTBF, and I've gotten this question sometimes, hey, I made this change and my system's performing worse, but my MTBF is longer. And it's because everything else is worse. Yes, you can increase your MTBF, but at the cost of downtime and at the cost of unavailability. So it's if you were looking at it in a vacuum and all you wanted to do was longer MTBFs, you could just take my time, but then you're paying for it with less usage time, like less usefulness of the part. So
Yeah,
that
no,
was
that's
my point.
absolutely
Yeah.
right. And no, that's great. Thank you. And it's absolutely right. And it is actually something also that's going to come up with this example as well.
Right.
So,
Sure.
but yeah, that's a very good point, and probably better as you have done to make it now rather than wait till later. But
Right.
yeah, so MTBF on its own may be of limited use, but as we'll see, it's not on its own. There are other parameters that you'll be using to weight those decisions as well. Then let's take a look at some of these, what I've called more realistic examples. Now, I've got this little box on the right, just showing you like a block diagram. Not really of great relevance to what I'm talking about right now, other than that it illustrates the fact that I'm using simulated data to basically create data for my calculation, because I don't have populations of components that I can run to failure here in the office to do these calculations for you. But through the magic of Availability Workbench, I've been able to simulate some failure data that I can use to show you how some of these calculations work and where things can go wrong as well. So I have an example that illustrates the impact of wear out on these calculations. If we fail to be aware that wear out is a thing in our data, we'll see how that can manifest itself. We'll also take a look at the calculation of mean time to failure using running time versus service time. And then I'll have an example of calculating MTBF, but using that, what I would consider an incorrect definition of repair to failure instead of failure to failure. There'll be a fourth example a little later, but I will start with these three. So first of all, calculating mean time to failure with wear out data. Now, if you will forgive me, I'm going to show an Excel spreadsheet very briefly. Now, obviously, I'm not going to read out every number to you. What you're seeing on the left there are simulated times to failure. So I had a population of maybe 100 components, and I simulated when each one failed. And there they are. There's my times to failure, one for each component. And I simply, added up the running time, the way I'm supposed to, so not the service time, but the running time, and divided by the number of failures. And I get 4380 hours. So this is on average how long each of these, or how long one of these components lasted for. But is that telling me the whole story? Well, let's take a look at a different type of analysis, done different on the exact same data, but in a different way. So I'm going to bring Availability Workbench over. So this is our simulator tool that has this viable analysis tool built into it as well. So I've imported the times to failure, and I've done a line fit to this data, basically assuming random failure, as my mean time to failure calculation does. My Excel calculation assumed random failure, so I've analyzed this data as a viable, as if it's random failure. You can see there it's giving me the same result, 4,308 hours. But I mean, even at first glance, that doesn't look like a great fit to the data, because actually it looks like there's some kind of wear out going on. If I have a look at my failure rate as a curve, this might be a little easier to understand. So I can see approximately how the failure rate changes over time. So it's pretty constant early on, but then eventually stuff begins to wear out. And my trend line is nowhere near it. So technically it's the mean time to failure, but it is not telling me the whole story. Maybe I would need to resort to something a little bit more complex if I'm going to spot these wear out. So the exact same data, but this time fitted using a biviable, so two viable curves. I won't go into detail on the maths of that, but basically there is wear out here. After about 6 months, this thing starts to wear out and the failure rate increases. Or if you prefer, the mean time to failure decreases. So if I were to simply add up all my failure times and divide by the number of failures, I would not get the right answer. This is probably going to be more of a problem if you're dealing with components that do experience wear out or assets that experience wear out over time. Bearings, maybe, we've mentioned a couple of times. But if you're dealing with maybe electronic components that probably will wear out someday, but only over a very long period of time, maybe it's fair to consider failures to be random. But it is something that's worth considering when you're analyzing your data. So what was my next problem? Well, my next problem was that the issue with the way the internet was telling me to calculate mean time to failure using the service time instead of the running time. So again, as a reminder, because there's a lot of terminology being thrown around here, service time is simply the observation period multiplied by the number of components that we're observing, so the total service time. Whereas running time is the total amount of time that those components are operational during that observation time. So of course, excluding any time where the component has failed, which might be most of that period if it's a non-repairable failure, which in this case it is. So what difference does that make? Well, I'll bring up my next Excel spreadsheet, which is this one. So again, there's my time to failure. So that's simulated times to failure. Here on the right is the time after the end of the service time. I've kept that in my spreadsheet for a reason, as I'll show you. This is the time to failure, and then this is the time from the failure to the end of my observation period. So you can tell from that my observation period is 1 year. So if I do my MTTF, my mean time to first failure calculation the right way, this is the result I get. So I'm adding together all of my failure times, and then I'm adding together all of the service, all of the running time of the components that did not fail. I had a population of 100 components here, like in my last example. You can see here, only 61 of them failed. 39 of them made it to the end of the observation period without failure. So I'm including them in my calculation as well. So I add up the failure times, I add up all the survival times to get the total running time, divide by number of failures, and I get about 9,000 hours. Compare that to the result that I get if I simply add up the total so-called service time, so 1 year multiplied by 100, because I've got 100 components, and divide by the number of failures. That is wildly higher, much more optimistic than my running time estimate. So you can see straight away what the difference is there. But again, I can drive this point home by comparing that with viable analyses as well. So if I look at my viable analysis of the failure points from that same data set, there is my result. So I've got my 61 failures, and if I can show you quickly, 39 right-censored data points, 39 survivors that lasted for 1 year with no failure. They're included as so-called suspended data. And you can see the result is essentially the same, which is just here. So you can see that near enough, 9053, 9053, two completely separate analysis methods coming up with the same answer from that data set for the mean time to failure. Can I, in some artificial way, reproduce the incorrect result? How can I get that from doing a viable analysis? The answer is yes, I can. Here is the same data set. At first glance, looks the same data points. but the mean time to failure is now 14,000 hours, like my so-called incorrect result from Excel earlier. How and why is that? What I had to do, look down here, scroll down, there are my 39 survivors, but I've also included all of the service time, all of the time from where a component failed to the end of the observation period. I've erroneously included that in my data. These are phantom data points. There's no survivor associated with any of these data points in my actual data set. I've had to add them in to replicate that service time calculation. So that, again, it just drives home that service time over number of failures calculation is going to give you an overly optimistic mean time to first failure. Really, it should be running time. But then, of course, that treads on the toes of our MTBF definition of running time over number of failures, which means that MTBF must be something else. The last example on this slide, calculating MTBF using the repair to failure definition. Here you can see I've got times to failure. This time, in order to make sure I'm not biasing my result in any way, I'm not doing it for individual failures. This is the same failure, repair, failure again, repair, failure again. So it's just one item sequentially failing and being repaired, failing and being repaired. This is what MTBF is supposed to be about. Not lots of different failures, but one thing, failing and repairing over again. So there are all the failures of that one item that is being repaired and failing again each time. There is the running time divided by the number of failures. And I'm getting 8896. If I do a line fit in Viable, I get 8896. Even though I've not clicked any buttons in my Viable analysis that says this is now a repairable component, there's no difference in that calculation. It's doing a line fit and arriving at the same result of what is supposed to be a mean time between failure calculation, but is in reality a mean time to failure calculation because of all of those assumptions about no wear out, about random failure, and how each startup is indistinguishable from the last. It's no different from having the 91 failures of identical but separate non-repairable components. The outcome is exactly the same. So that illustrates that those two definitions that we have of mean time to failure and mean time between failure are fundamentally the same thing, which means, again, mean time between failure must be something else. So finally, mean time between failure, is it just not really a real thing? Are we saying that actually the only real parameter here is mean time to first failure, mean time between failure is some kind of illusion or a lie, or we should just throw it out because it's not useful? That's not the case at all. All the problems here don't come from MTBF itself, but rather our confusion over what it means and how it's useful, what it should be telling us. Mean time between failure, as we said, all the way back at the beginning, is intended for use with repairable systems, and it is the time from failure to failure of a repairable system. So it includes that repair time. So the thing here is that systems will almost always have redundancy. A system is not a component. It doesn't just work or fail in the same way as a single capacitor, a single bearing, a single pump even might work or fail. It's made up of lots of different elements, lots of assets, lots of components, and it might take multiple failures in order to bring that system down. So we need to think in slightly more complex terms about how MTBF is calculated and about what it's telling us. in this scenario, the failure rate of the system is not constant. Failures of a system of any complexity are not really random because of the interaction of all of these different component level failures, components that themselves might not be repairable and have to be replaced. The system itself isn't being replaced, it's just failing, coming back online again. So we need to do a more complex calculation to accurately estimate a mean time between failure. And because of this problem that we have about the mean time to repair, and we said, well, if I want a better mean time to fit between failures, can I not just inflate my mean time to repair? Sort of, you could do that, but the impact of it would be very much diluted by the redundancy. And of course, Joe's point earlier about MTBF not being used on its own. So let's take a look at one last example to kind of illustrate some of the points that I'm making here. I'm going to end my show and I'm going to bring up a little fault tree. So an isograph demo would not be complete without looking at a fault tree. So this is just a fairly straightforward fault tree. There's AND gates and OR gates and events representing random failures where components are replaced if they fail. So you can see there are events that have failure rates and mean times to repair throughout this model. So if I run an analysis of this model, take a look at the result from it. So there's my, I'll take a look at the cut sets first, just to illustrate that this is not a particularly huge fault tree. 87 cut sets, it's reasonable, but not excessive. You do often see them with hundreds or thousands of sets and more. So this is not a very complex system. Many of the minimal cut sets only have a couple of events in them. So even the levels of redundancy here aren't huge. This is not a complex system at all in many respects. So in my calculation, the program is telling me that the mean time between failures is about 1.011 years. So just over 1 year is the mean time between failures for this system, the mean time from failure to failure. What happens if I go in and I just decide, you know what, easiest way to get a better mean time between failure, let's say all this stuff actually takes 24 hours to repair. So I'm doubling the time to repair, I'm tripling it. In one case, I'm multiplying it by 6. I'm increasing the time taken to get this system back online or get these components replaced when they fail. I'll run my model again. Take a look at the result. And the difference is fairly small. And in fact, as Joe pointed out, the unavailability of this system will deteriorate if you increase the amount of time to repair any component therein. So if you were to say see an improvement in MTBF, but a deterioration in the availability of your system, those two things together might tell you what's happening, that it's simply taking too long to repair some of the failures that are happening therein. Mean time between failure is a useful measure of how often a system is failing, and used in conjunction with unavailability, or if you prefer, the availability of the system. Then what you get is an idea not just of how often it's failing, but whether or not the downtime is too great. Maybe the repairs are taking too long. So you wouldn't use mean time between failure on its own. If you were to do so, yes, its usefulness would be limited, but in conjunction with that downtime, in conjunction with that unavailability, then you start to see where the patterns are emerging of where that downtime, where those problems are coming from. So just to conclude, mean time between failure, as we've established, it's the average time from failure to failure and should not be confused with mean time to failure, which is the mean time to first failure of a system. Mean time between failure should only be applied to repairable systems, whereas mean time to failure, mean time to first failure, is in general applied to non-repairable components. Mean time between failure, yeah, it's affected by MTTR, but the impact can be greatly reduced by redundancy in a system, and perhaps most importantly, MTBF, mean time between failure, is not used on its own. It can be a useful measure of how frequently a system fails when used together with the availability, or unavailability if you prefer, of a system. So just to finish off, we'll take some questions. And I think, Jeremy, you had a couple of words you wanted to say as well.
Yeah, thanks, David. That was a great presentation. We are just about out of time. Let me see. Let me just look at the questions really quick. Most of the questions we'll probably deal with after the meeting. So anyone that asks questions will be contacting you. Most of these would take a little bit more time than we have left in the meeting. So
Definitely didn't do that deliberately.
no, that's good. It's a complicated topic. You did a great job presenting it, David. Thank you. If you want to, can you just flip to the next slide about training?
Yeah.
So as we saw, we have David. Joe is on the line. He's he's in our U.S. office. He's kind of David's counterpart in the U.S. We do offer training courses. I wanted to introduce this because I haven't introduced it in the past, and these aren't the David and Joe run most of the training courses, all the training courses basically, and these guys are very fluent in these topics, and they've been around for a long time. So the training is very beneficial, not only on theory and math, but on practical ways to use the software to achieve the goals that you want to. We do a lot of our training sessions these days are online. We can come to your location if you want kind of a in-person training session, and we do offer training course certificates once you've gone through the training course, so it helps with your extended learning. On these on the training courses, I just put my own email in here if you have any questions on that. But you will be getting a follow-up email on this webinar, and if you want any more information, just put it into some of the questions that we're asking in kind of that follow-up poll. Joe, or David, is there another slide after that?
Nope, that's it.
No, that's it. Sorry, I should have had a finishing up slide for the for the webinar. For our next webinar, we have a great topic actually, and a guest speaker for the webinar as well. We're going to be talking about cost benefit ratio, which is a very interesting topic. It's basically the cost of doing maintenance versus running your system to failure, and it's also it's an interesting in-depth conversation on which you should choose and why you should choose it. The invitation on that will be going out soon, so watch for that invitation and sign up if it's something that you're interested in. Otherwise, like I said, you'll be getting a follow-up email. Please give us any feedback you have, any questions. If there's topics that you would like to see us cover in this series that we're doing this year, please let us know. We can't, of course, cover all the topics, but I have been getting great feedback from people from these meetings on things that people want to see. But I appreciate I appreciate you taking the time to attend our meeting. Thanks, David. It was a great presentation. I appreciate it. Thanks, Joe.
Thank you everybody for coming. Thank you, Joe.
Thank you, David. Yeah.